Welcome back to the next video, everybody. Today we're going to be talking about Kähler differentials and how they relate to the relative Zariski tangent space. So the setup is R will be a coefficient lambda algebra, where lambda is a fixed coefficient ring. Omega C of R over lambda will denote the R module of continuous Kähler differentials of R, which we refer to from here on out just as omega of R over lambda. For a discussion on the basics of this module, you can see Vakil's book, you can see Hartshorn's book, you can also see chapter 5 of my playlist. But be aware that if you do look up information on this in generality, we are dealing exclusively here with topologically profinite complete Noetherian rings. So we're going to demand that our differentials respect the topologies in question. So the C means continuous. Okay. So intuitively, though, what is this module? It's the R module that sort of captures the maximum amount of first order infinitesimal information about the ring R. So more formally, this module is equipped with a continuous derivation, which is a lambda module homomorphism satisfying the product rule. We'll call that map D from R to omega of R over lambda relative to lambda. So here, D lambda is 0. And the way I think of that is just derivatives of scalars are 0 from calculus class. Okay. It's universal with the structure, which means it's the universal topologically profinite R module equipped with a continuous derivation from R relative to lambda. Another way of saying this, maybe that's more enlightening and direct, is that for any topological R module M, there's a canonical isomorphism from the R module homomorphisms of omega of R over lambda to M, with the derivation, the lambda algebra derivations from R to M. So I like to think like this omega here is turning derivations into module maps. Okay. So what is this here? This again is just the R module of continuous derivations from R to M. Okay, so concretely, you can actually concretely construct omega of R over lambda. So the first thing to realize is that if you take the completed tensor product over lambda of R with itself, this is again a coefficient lambda algebra. And then you have a multiplication homomorphism mu from that tensor product to R, that it sends x tensor y to x times y. This turns out to be a surjective homomorphism of coefficient lambda algebras. We'll let I be its kernel. Now mu is continuous, so I is a closed ideal in the domain here. We have also a continuous homomorphism of lambda modules, which we'll call delta from R to I, and it just sends R to R tensor 1 minus 1 tensor R for each R in big R. But R tensor R is Noetherian, so I squared is actually a closed ideal. There's a topologically profinite R tensor R module structure on I mod I squared, and that factors through a canonical R module structure on I mod I squared. Why? Well, you have a topological identification of R tensor R over I with R, which you can check. And the map D from R to I mod I squared obtained from delta by projection from I to I mod squared. So you just take delta and follow up with projection. This is actually just seen to be a continuous derivation relative to lambda. And it's seen to be universal for continuous derivations of R relative to lambda. In other words, you can take omega of R over lambda to just be I mod I squared. You're linearizing here. So you're taking things and killing off square parts. Okay, so this isn't really too surprising. Here are some examples of this in action. Let's let P be lambda double bracket x1 through xn. This kind of power series ring. What is omega of P over lambda? It's canonically isomorphic to the free P module of rank n generated by, of course, dx1 through dxn. And the usual derivation here, d from P to omega, is just the standard differential d from P to P dot dx1 plus blah 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 plus p dot dxn on the power series. So it's the usual kind of derivative. Okay, and of course d lambda is 0 for all lambda and big lambda. Okay, here's another example. Let's let R be that same thing. So omega double bracket x1 through xn mod out by the ideal generated by polynomial or power series f1 through fm. What is omega of R over lambda here? It's the quotient of the free R module on n generators dx1 through dxn by the sub R module generated by the images of the derivatives df1 through dfm. What do I mean by that? Images under what map? You just project, right? So you take p dot dx1 plus blah, 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 plus p dot dxn, and you project to r dot dx1 plus blah, 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 plus r dot dxn, just by sending each p kind of coefficient here to r by taking the quotient by this ideal generated by f1 through fm. Okay, so here you see that omega of R over lambda is a finite type R module. Here's another example. If R is a coefficient lambda algebra, there's a natural identification between the K vector space omega of R over lambda tensor down to K with omega of R over lambda completed tensor product over R down to K, and the cotangent space T star of R over lambda from the previous videos. So a proof for all these things you can see Bakil's book or Hartshorn's book. Okay, so this is actually important for us. We're going to seek to kind of generalize this today, and we're actually going to want to get rid of the star here. All right, so let's bring back the functor D from the previous videos, just some covariant functor from some category to sets. That functor is pro-representable by an A augmented coefficient lambda algebra R. When the functor D from the previous videos, so just some covariant functor from C to sets, is pro-representable by an A augmented coefficient lambda algebra R, D does not satisfy the the tangent A module hypothesis from the last video. Okay, and so what you have then is the dependence of the tangent space of D on the representation map from R to A. Okay, so because of that, we'll sometimes write T sub dA equals T sub D rho, where rho is this map from R to A. Okay, and then the following comes from definitions. What is TD rho? It can be identified with the subset of lambda algebra homomorphisms from R to A bracket epsilon, consisting of those lambda algebra homomorphisms whose composition with the natural projection from A bracket epsilon to A is just rho itself. Okay. Here's another way of obtaining TD rho, though. So proposition, let D be represented by the coefficient lambda algebra R, i.e. D is just the functor D sub R from more towards the beginning of the chapter. So it's dr of B is maps from R to B. Okay. Let A rho be a pair such that A is a coefficient lambda algebra in C hat lambda, and rho from R to A is a coefficient lambda algebra homomorphism. That is an element in D of A, which is lambda algebra maps from R to A. Viewing A as an R algebra, there is a natural isomorphism of A modules between the following sets. So A module homomorphisms from omega of R over lambda, completed tensor product over R with A, comma A, and the tangent space TD rho. In particular, if A is K and rho is rho bar, some residual representation, then the K maps from omega of R over lambda, completed tensor product with K, comma K, is nothing but TD rho, actually. Okay, and so we don't really need the star here, actually. So for a proof of this, you can see Cornell, Silverman, Stevens, page 276. So another, like, the upshot here really is just these tangent spaces of these functors can be thought of in terms of differentials, to the surprise of almost nobody, right? I mean, that's kind of where we're headed with this intuitively. All right, we'll keep pushing on next time and look at more of this differential stuff. I'll see you then. Thanks for watching.